Okay, for people who are joining this live stream, this is a meeting about incremental language development for Wolfram language, and we are heading towards release of version 12.2, so there will start probably to be more of these meetings and about all sorts of things. We have a variety of topics today. Let's start with new properties in axiomatic theory. Okay, so let's remind ourselves, and I had sent in some things that I had looked at with Mano, but let's remind ourselves what, wait a minute, we first of all, we talked about having a data set thing. So we want to have something where we say something like this, the axioms, this is the default, but I think we want, right now, we don't have any way of asking for everything, right?
Right, that's correct.
So, okay, so first thing we need is data set, which is going to work the same way that data set for entities works. By the way, is it obvious? Oh, I see. The reason that we didn't want axiomatic theory to be an entity property system is that we also had this whole operator adventure here. Right, so these are parameterized entities.
Yes.
Does anybody have an opinion on whether we should in fact move this to an entity property framework? Because I mean, we do have parameterized entities like that. Is anybody here from who knows about that stuff?
For example, function spaces.
How do those work?
So like LP spaces will have the standard name is a list and have a formal symbol for P. And then you can do replacements and the properties change accordingly.
I mean, I do kind of like having this axiomatic theory head, but it does seem like this will fit in better with the entity property framework. Jose, do you have an opinion about this?
Well, the fact that the third line takes theory, property, it's imitating that. But it's true that we don't have an entity head around things. We could add it and keep axiomatic theory.
Yeah, that's a reasonable suggestion.
When we designed these, we were thinking whether this should be axiomatic theory data. And I don't remember right now the arguments, but we decided not to go that route.
Right. I think it was because of that second argument.
But it's not really a second argument. It's like an extended first argument.
Oh, I see it. I'm sorry, yes. Is Jonathan here? Does he remember?
No, he's not here.
Was he invited?
He was not.
We should probably invite him since this is his function. Could somebody see if
Yes.
they can track him down, please?
Yeah, sure. I can do it.
Okay.
This is again the same pattern of we were discussing last week for projections and calendars, of having a named thing and then an association in the second argument, which we added last week for projections and calendars.
Second argument or in a sublist or in a list?
We were discussing both things. And since then, I have been thinking quite a lot about it. And converting the list of rules into an association of rules is very easy, and I find it useful. Converting the whole thing into an association, I'm having doubts.
Okay, so are you supporting for the calendar thing something like this package of name, comma, association? Is that
Exactly.
right?
Yes. But
well,
not
pattern we should use. Yeah, go ahead.
Yes, we discussed a second possibility, which was that even the theory would be inside the association with some theory name or something like that.
Mm-hmm.
But I think the theory name from the options are very different, so they deserve being treated differently.
All right, fine, which is what you want to do for calendars as well, is what you're basically saying.
Exactly, yes.
All right, then fine, then let's make this a pattern for other things too. Mm-hmm. Okay, let me look at, I had done some stuff when I was talking to Mano. Where is that stuff? Should be in working materials. Axiom Systems 01 maybe. Okay, so these were some things that we discussed. Data set we talked about, notable theorems we talked about. Now I put in some more notable theorems for Boolean algebra, right?
Yes, and those have been added already to the system. They are in 12.2.
Okay.
Yes. By the way, Ian detected some small error, some name. Which one was it, Ian?
Ian, what did I get wrong?
Always true, always
always
false.
dropping true and always dropping false.
Yes, those were reversed.
Oh, terrible. Thank you for noticing. Okay. So this was some. Okay, so one of the issues is, what are we using for the operators? Like the not operator or the this is, well, in this particular case. Okay, one of the issues is we need some more meaningless operators, right? Does anybody know how to install those? We haven't installed those in years. Do you know what I'm talking about?
Yes, like circle times and this type of thing. Yes. Yes, those can be added. And for example, we are adding a new one in that direction for Roman's combinators.
What is Roman doing with combinators?
Yes, so he wanted, how is it called? Combinator apply.
Oh, yeah. Oh, gosh, right. I need to know about that because I'm trying to write this blog post. You know, it's the 100th anniversary of combinators in December.
Right.
We're trying to write something about that. And we've been tracking down the mysterious history of Moses Schoenfinkel, creator of combinators. We have had great success. It looks like we're actually finding yeah, we're actually finding some information, which is a surprise. In the bizarre archives of both Hilbert's archives and in the archives in Ukraine. Anyway, okay, that's somebody. Yeah, okay, never mind. Okay. So one question is, as we convert these things, like, you know, we've got only a limited inventory of meaningless operators. I don't think negation is very happily a square, but there's a limited number of prefix operators we have. You know, meaningless prefix operators. Am I making sense?
Yep. So something we could use too here is inactive. So negation goes to inactive of not. Things like that. So it will print correctly.
Interesting idea. I mean, I like, though, for something like this, I don't want to have NAND in here. I like having the dot here. But I think yeah, that is an interesting idea. Is there anything that goes wrong with using inactive for those things?
No, I don't think so.
Oh, I'll tell you something that's the problem. The problem is that when you state the theorems that you're trying to prove, the propositions you're trying to prove, you have to have the same operators in there, and that's a nuisance.
Sorry, what do you mean?
Well, I mean that if I'm trying to prove, you know, A dot B equals, I mean, with this, right? I'm going to say, find equational proof. Of this, but I'm now got to put in, I'm going to say P circle, I mean, P, you know, I've got to have the same operator, right?
Yeah.
In my, and if it's, you know, if it's a whole elaborate thing with, you know, having to find that operator, that's a big nuisance.
Yes, we would have to write manually in the theorem inactive of NAND.
Or do some kind of post-processing to check that, you know, if you've used operators that already exist in the theorem, then just inactive them.
But it may be too late because
it may have just evaluated.
It may have evaluated, but that should only happen for theorems that are kind of trivially true, right?
It's a bit dangerous because you never know whether something is going to pre-evaluate. I mean, things like and, not, do already things.
What the heck is this? So wait a minute. This is the parameterized entity for function space. Is there a print form for this?
Yep.
That's kind of magnificent. What is this? This entity? I see. This is a parameterized name of an entity that works like this. Well, I think that's a good thing to use for these axiomatic theories as well. But I think we should continue to advertise it through axiomatic theory. But if we can hook it up to the entity property system, that would be a good thing. All right. So, and look, what we need to get as Mano goes through these different theories, she should aggregate, what the different operators that would be convenient to have are. And then we can do one pass trying to add, basically at this point, we could add any Unicode character. Okay, we're going to need two things. So just to understand what that's, we haven't, as I say, we haven't added things for this for like probably 20 years. At least not significant numbers of them. Okay, so this is a character name page, and it maps to a certain Unicode character, and that's the important line, is interpreted by default as blah, 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 and then it needs a precedence as well. Make sense?
And associativity and various things, yeah.
Right.
One thing that would be nice as a general solution to this problem would be extending formal symbols to also include operators.
You're asking for an arbitrary parser. That's hard. Right, because what you want is an infix. Look, there is a way to do it. Okay, so this is another way to do it, is that we could be using things like, something people very rarely use, but this form here. Because you want something infix, right, Jonathan?
Yes, maybe, but
perhaps Jonathan is talking about a formal not, which will typeset exactly like not, perhaps with a dot underneath.
Right, exactly, right. I don't see why it's more complicated to have formal plus than it is to have formal A.
No, it isn't. It isn't. But the point is, Jonathan, what's really needed is theories for which we don't have a built-in concept. Like, meet and join. We don't really have formal concepts for those, or successor. We don't have an existing concept for that. You see what I'm saying? Like don't
we have wedge and V?
We do have wedge and V. Wedge and V.
Yeah.
But my point is, there are going to be theories for which we do not have the operator.
Sure, but that's not an argument against having formal operators. That formal operators will make that easier to deal with.
No, I know, but the other point is that the point that I'm trying to make in these axiomatic theories is, look, axiomatic theory is already confusing enough for people. The concept that this thing is known to be NAND, for example, which isn't even true, could be NOR as well, is super confusing, right? For a theory where there is only one meaningful assignment for an operator, you can do one thing, but I think in many of these, there isn't, so to speak. I'm trying to avoid the idea that it actually is the plus operator. Like, take pure arithmetic, right? We know it isn't necessarily actually the plus operator. It could be a non-standard arithmetic plus operator. That makes sense, Jonathan?
Well, yeah, but in each case, there will be a canonical operator. So I still don't understand why that's an argument against having formal operators.
Well, but what would it look like? You're saying a plus sign with a dot underneath it.
Right.
And how would you enter it?
Formal plus. / formal plus.
Yeah, but / plus probably doesn't even exist. It doesn't. Because it's just the ASCII character.
Yeah, but / A doesn't exist either. But that doesn't stop us supporting formal A.
Well, fair enough.
Aliases like escape $A.
Yeah, right. And we can certainly do that.
My question is, I still don't see how this is much better than inactive or plus, which will be then understood by many other things in the system.
Yes.
I agree.
Now, the thing is that we don't have a nice way to introduce inactive of plus. And perhaps that's the thing we should try to find out.
What do you mean?
Like, again, imagine that we have escape I plus, and
Yes.
that's inactive of plus.
Sure.
Interesting.
But then you're proposing that we potentially even change the defaults for these axiomatic systems to be inactive operators. But you see, look, take a look at this case, for example, right? What are you going to put in for that operator?
No, I wasn't going that far. It's just in case the user wants to use something that reminds him of what this is. For example, some users have complained that axiomatic theory does not know information about plus and times. They want to do proofs with arithmetic. Now, if we had those action systems for arithmetic operators, it might be nice to have that type setting.
All right. Well, okay, so one possibility then is that the second argument, what we're saying is that there are multiple choices for the operator assignments, right? There's default choice for operator assignments, but we might have a secondary choice for operator assignments that is, I mean, in this case here, we could have a secondary choice. Oh God, this is a mess.
Or at least we just allow the user to say plus goes to
Which we
inactive
already
plus.
do.
Yeah, we already allow that.
And I
Yes,
was,
but your argument before was that then it's difficult to write the actual theorems because we
Well,
don't
but
have
if they
short-
put it in, then they know what they're signing up for.
right, yeah, that's true.
My
By the way,
concern. Go ahead.
at least for all of the axiom systems that I've implemented so far, the axiomatic theory already if you request out the operator information, it already provides an interpretation of everything in terms of operators that currently exist in the language.
What is that? How?
So like if you ask axiomatic theory Wolfram axioms operators, it will tell you that NAND is interpreted, that center dot is to be interpreted as the NAND operator. And
That's right. That's this thing here that I filled in.
Yeah, right. My point is, in each of those associations, the left-hand side is a specification of a built-in Wolfram language symbol. There has not yet been a case. I agree we shouldn't preclude the possibility that it will happen.
There will be a case. There will be a case.
There isn't standard notation for it.
Right, but successor, for example, we don't have a standard notation for successor.
But Jonathan, what you have there on the left is string.
Yes.
Yes, right. But the string is
at least reminiscent of a standard Wolfram language name.
Right, but we could have perfectly a string successor.
Sure, that's right. That's why we put it in as a string, because we knew that was going to happen. All right, so the issue is, what is the default right-hand side there? Is the default right-hand side center dot, or is it something that looks like this? NAND goes to inactive of NAND. That will be another possibility, right? And so if I look at that, if I say axiomatic theory, that would be a nice autocomplete to, by the way, be able to have. If Devin, if you can report that to user assistants.
Yeah.
Inactive doesn't typeset nicely in data sets, or indeed in summary boxes.
That should be fixed. That's a bug.
Exactly, that's fixable.
Right, but which means that right now, if you try and use find equational proof with an inactive operator, it will look pretty ugly.
Okay, well, can we get that fixed? I mean, that seems like a rapid fix thing.
Yep.
Okay. So, I mean, that doesn't look bad, except that I don't like the fact that it's an actual operator there. Humph. And group theory, we definitely don't have. What is the right thing to represent group multiplication? It's not a times sign, for sure. I'm also worried about some of these things with built-in associativity and commutativity, actually. Some of these operators have built-in, well, the inactive version of NAND does not, right? It doesn't have its built-in commutativity.
Correct.
All right, look, go ahead.
We have small circle.
I know, but notice that small circle isn't a built-in thing. So I mean, what we have in the group axioms, right? If I ask for the group axioms here, and then I say operators.
Yeah, we don't use small circle.
By the way, we should switch around that autocomplete so it comes operators first before operator. We use circle times.
Right. I did suggest circle, small circle.
It's probably the right thing. An identity, what is that creature?
That's an over tilde 1.
Well, it might be better to use. The problem is we can't change this too much because people are going to start having code that assumes a particular, operator, because they're going to just say find equational proof with group axioms, and it'll assume the operator. We might be able to get away. It's still pegged as experimental. We might be able to get away with changing it one time here, and I do kind of agree with you that small circle will be better for this, or even just center dot might be better. Well, so let's make a decision on that. I would say center dot. What do you think, Jonathan?
Yeah, it's not bad.
Okay. All right. So let's come back here to. All right. So I think what we want to do is potentially. What I'm thinking is we might want to have a secondary thing here that says, I mean, that kind of thing, where that basically is bank switching. You know what I'm saying? That would maybe we have another property called inactive function operators that basically is this form as much as we can make it with inactive operators rather than with these arbitrary symbols. Does that make sense to people?
Yeah, we can do that. We would give an error for the cases in which we don't have the corresponding.
Well, we'd say missing, not available.
Would we use permutation product for the group case?
What are permutation products?
We have a symbol permutation product.
What the hell is that?
It's something you can multiply to permutations.
Circle dot, right?
It's not circle dot. Permutation product has its own symbol.
Oh my gosh.
Works.
The problem is what we're dealing with here is, yes, I suppose we would do that because permutation product would actually work between group elements, wouldn't it?
Yeah.
You had a concrete group element, you could actually do this.
Exactly.
So, okay, fine. So that would be what about for the inverse then?
We have permutation inverse. Or inverse
as a function.
As a function, yes.
But not as a piece of symbolism.
No.
Yeah, typesets as permutation power -1.
Well, but maybe that's useful to people. I mean, if they want something which is actually the inactive functions, why not give them that? Inverse arrow, that permutation power thing. It seems like a reasonable idea, actually. Because that way, what you can do is you can take any formula you have and you can convert it to a formula in terms of our semantically defined operators. And you just say activate and kaboom, the formula evaluates.
Right. Yeah, it might be useful to check examples, for example.
Yes. Well, so maybe there's a different name that we give as the second argument here. What should it be called? I mean, it's a version where... No, it's okay, actually. Inactive functions as that second argument there. Okay. All right. Where am I saving this, by the way?
You have a folder in your notes called Axiomatic Theory.
Okay. All right, so let's go over here now. Okay, so we've got inactive function operators. All right, so let's keep going here.
By the way, sorry, just a quick thing. I mean, do we not have a slight philosophical issue with essentially interpreting every group as a permutation group?
Perhaps, but that's the only type of group we can handle right now. So we don't have functionality for matrix groups.
See,
or
this is exactly the slippery slope that we're going down here, because there's the same thing as non-standard arithmetic, right? That these are purely formal axiom systems.
Right. This is kind of my issue, right? I mean, so I know, obviously we have Cayley's theorem, and so it's a reasonable interpretation to think of these things as permutation groups, but that's implicitly assuming that the group is acting on its own set of elements, which won't be true for a general formal group.
So I see this as representing some sort of model. So you have the general theory, and then you want to play with examples, and then you fall back to some potentially bigger theory.
Okay, look.
But the choice of, I don't know, my view is that the choice of operators should not imply a particular model.
Yes, but unfortunately, that's what we have. Okay, Jonathan, this is the logic, okay? If you've got like circle times, it means nothing. It implies no model, right? As soon as you put in there inactive NAND, it implies a model, right? Right there, whatever, Stone's theorem or whatever it's called, you're just dealing with the standard Boolean algebra thing, not the 2 to the n sized algebra.
Right. No, I agree, which is...
So I think what we should do is this. I think we should say axiomatic theory and then inactive function model, let's say. Actually, I mean, in general, the right thing to do is to name the model, right? So there might be a default model. And by model, all we're doing is we're filling in function names that correspond to... In fact, look, the obvious way to do this is to say essentially typical models, and then to say, or standard model. Or standard model operators.
Right, exactly, because we're not defining a model. We don't have a domain of discourse. We're defining part of a model.
Right, so the standard model operators would then be, this is so weird. I mean, so we would have NAND goes to inactive NAND. Right? Or in the group case, you can argue about what you want to do with the group case. So then what we would do here is we would say something like, somebody's commenting on our live stream that standard model means something in physics. Yes, that's an amusing thing. Oh boy. The real question is, will there come a time when in our interpretation of Rullial space, the standard model is the standard model? Okay, Jonathan at least should have found that amusing.
Yeah, I do wonder at what point will the standard model be an axiom system in axiomatic theory?
Right. That's the and then how long will it be when it is?
Right.
Okay, but in any case, I think the right thing to do here, this is a nice idea. I think you give the axiom system and then you potentially give the model here. And in a sense, by giving the operator assignments, that is a version of defining the model.
Perhaps the property that you wrote there, NAND goes to inactive NAND, we could store that as NAND goes to NAND. And it's when they are inserted that the inactive automatically gets there. Because the model doesn't care about inactive.
I see.
So,
well, how does it know when to insert it?
Not there. I'm referring to the line 5 lines below.
So I see. I see. In this line here.
Exactly. So the model doesn't care about inactive. It's when you are going to replace the internal operators that it does care.
Okay, fine. So then what would happen here is, okay, here's what I suggest. I suggest that we say symbolic. The default is either symbolic model or just symbolic. And then we also have standard model. And the standard model works like this.
But it should be symbolic model operators, not symbolic model.
No, I'm saying for the second argument here, for the second element here.
Right, but unless we're defining a domain of discourse, it's not a model. At best, we're defining an infinite family of models.
And we can't define a domain of discourse unless we define types, presumably.
I think that's a bit too much, Jonathan. So, for example, for permutations, we just consider all possible permutations. There is no need to specify a degree in the system. We can multiply permutations of different degree. Or for numbers, we just consider all numbers. We don't have to say, I'm working with these numbers.
But you're still implicitly assuming, in the numbers case, right, that your domain of discourse is all numbers.
Yes, but I think that's implicit in the operator. Once you say, I'm using plus, you know which numbers you are using. Or once you say permutation product, you know which permutations you're using. Those supported by permutation product.
And you say NAND knows that it is expect Boolean operators and things, but Boolean, true and false and so on.
Exactly. In a sense, we have type by documentation or type by implementation, if you want. It's what the function supports.
I see your point. Okay. So the domain of the function is the domain of discourse, just implicitly.
Exactly.
Okay.
Okay, so then the two things that we would usually support are standard model. So this would be, and then we could have another thing called model operators or model notable models. Now for group theory, we could start listing groups here. And then we would say, standard model arrow, and then we've got basically the mapping from our name for the operators to the name that is going to be used there. See what I'm saying? Right. And then, so then you could type in Wolfram axioms, comma, the default would be symbolic model, but you could also say standard model there. I think this works. So that's irrelevant. The inactive functions that model is irrelevant. Now, operators here would presumably that will give it relative to the model that you are referring to. Okay. Now, but these names on the left-hand side are purely, honestly, that name isn't really right for Boolean algebra. What is that name for Boolean algebra, really? Unfortunately, that is right, because otherwise we have the and or not of Boolean algebra. So that's what we have to do for Boolean algebra. So that's fine. Okay. All right. Makes sense to everybody? Let's move on. Everybody good here? Mano, you understand?
I think so. I'll loop back with Jose as well. But What about the syntax for the properties we already discussed, like the citation, for example?
Yeah, let's go through that. Okay. Axiom names, that's the next can of worms, right? How to deal with that. So let's pick, let's look at the group axioms, for example. Well, actually, let's do, what's a good example? Where the field axioms, don't they have names? What?
You chose precisely the one that should not be there. We removed those because they were not expressible via equational logic. But now they should be expressible in Jonathan's extension. So
We can now handle implies.
right. So
All right. So some of those axioms have names, correct?
I think they can be named.
Okay, fine. But so how do we deal with, look, maybe what we should do, I mean, one thing we could do is simply say, we could have a property called named axioms, in which we repeat the axioms, but with their names. Or we could say axiom names, and we could either do something where okay, what do we want to do here? We could have something which is in parallel to this list. We could have something where this list is repeated, but with names. What do we want to do?
I'd suggest to name a property that returns an association with named actions, and the values are the axioms themselves. I don't know whether it should be named actions or axioms association, like we do in entity, property, value, association.
I see, where this thing now is a named version, where just the axioms, the one property is just the axioms. Yeah, there we go. Axioms, that's a good idea. I like that idea. Axioms association. I like that idea. And then we'll name the axioms with sort of standard, things like this. Now, the only issue then is common names for the axioms. If you want to make a table, for example, how do you do that?
Well, I can imagine that some actions will be obvious, like commutativity, associativity, etc. Others we will have to decide and try to be as
no, I know, but I
consistent
mean,
as we
look, De Morgan law.
Mhm.
De Morgan law 1, blah blah blah. Let's say, okay, that's not
Yep.
usually an axiom, but it's going to look like that. It's going to be much more of an entity-like thing. Now, look, if these were entities, if every axiom was an entity, then we're home free. Then we've got a common name property for the entity.
Oh, you are thinking of axioms that appear in various axiom systems.
No, I was thinking of just naming, I was thinking of actually entityifying the individual axioms in an axiom system. In addition to entityifying, look, one thing we could do is we could have an entity axiomatic system, ring axioms. Then we could have an entity axiom, standard name ring distributivity or something. And then that would get to have a name, would show up as an entity, and then you could ask for its common name, and then you've got its common name. See what I'm saying? This is the right way to do it, I'm afraid, is to make all these things into entities. Because then what we've got, if we did that.
I seem to recall when we were first designing axiomatic theory and we discussed the possibility of having it be an entity store. The argument for not doing that was precisely because we wanted to be able to do operator overrides and things like that.
Well, the operator overrides thing, Ian has convinced me that there's another solution to that, that it's possible to have parameterized entities, which it wasn't possible at the time when we designed this.
Okay. then maybe we make the whole thing an entity store.
I don't think this works in entity store.
Which works?
The parameterized entities.
That's a custom parameterized entity.
Yeah, that's through Wolfram Alpha. I don't think you can have lists of standard names in a entity store.
So
No.
here, I think the question here is whether in this list, comma association that we were planning before, perhaps it's only the string in the first argument that should be an entity. It's the abstract thing. Who cares logically about which names we are using for the operators?
No, I'm not suggesting the operators be entities. I'm suggesting this thing be an entity, and I'm suggesting that the naming the axioms. I mean, in other words, if we did entities for axioms, then we could, for individual axioms, then we could do something else that would be quite nice, which is to just be able to put in a single axiom rather than a whole axiom system into axiomatic find equational proof. See what I'm saying? If we had something called entity, axiom, ring distributivity, that just becomes an axiom, which you could feed in and will get translated into whatever that axiom is for and you know, maybe what we do is we say, if you want to parameterize this axiom in a different way, you can say, for now at least, axiomatic theory of that entity, axiom, blah, 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 comma, and then the operator assignments. And
Right.
that's our way.
So what I was suggesting is to do the same thing for the action theories. So the fact that the operator assignments are outside the entity always.
Yes, I think that's fine. I'm sold on that idea. But then what I'm suggesting is that in the axioms association, that what we do is to use the entities for axioms, for the axiom names. See what I'm saying?
Right.
But we still use strings for the we're still using strings for the operator names. I mean, we could have a thing called group theory multiplication that is an entity there, but I think we shouldn't bother. What do you think? Yeah. Okay.
I think that's too much.
Okay. Fine. All right. Okay. So then we've done with those. Okay. So now, that gives us a solution for axiom names. So Mano is making up, our kind of standard names for the axioms. Which we should make up a list. We can check them off. Okay. Description. Okay. I think that should be an English language description of what this axiom system is. Like in this case, it would say minimal axioms for Boolean algebra. Okay. So that might be, where am I putting this here? Okay. So other properties. Okay. So description. If anybody object to this, I think that should just say, minimal axioms for Boolean algebra. And we could say things like, Hilbert's 1923 axiom system for geometry or something. I don't know what it would be, whatever it is, things like that. The thing that identifies them within the mathematics literature. Make sense?
Yep.
Okay. Reference. Now, Ian, I think we have a standardized way with our upcoming bibliographic reference system. We will have a nice canonical way to do this. But until that's the case, what are we doing for references in other mathematical structure things?
I don't know, 20%.
Okay, does Ian know?
I think it's all over the place. Like in the geometric scene entities, we just have strings with.
For what?
For like formulation sources.
Okay, so tell me the name of one of those. So geometric scene, and then what?
Do Pythagorean theorem.
Why does this not autocomplete? Okay. And now what do I do?
The property you want is formulation sources. That's not
That's
good.
really bad. Unprocessed arrow false. What the heck is that? What is nested grid? What on earth is this? This is garbage.
This is supposed to be a list of strings. I'll look into this. It's supposed to just be the string Euclid elements, book 1, proposition 47, 300 BC.
Okay, well, this is kind of cruddy.
Yep.
Okay, so I don't know the status of the Michael Allen project to do symbolic bibliographic citations. Okay, but we should make something which can fit into that future system. Okay, so Mano should find out what is done on that system already and should put things in here which are in that format, probably as associations. And we'll just use the raw association for now, and later on we'll have the wrapped association. Make sense?
Yep.
Okay, then I think we want question on a live stream from Parmenides, perhaps not the original Parmenides. Is the equational logic the same as Dijkstra's equational logic? I have no idea. Does Jonathan know? I didn't know Dijkstra even worked on those kinds of things. I think there's only one kind of equational logic, but I don't really know.
There are multiple, a bit like with first order logic, there are multiple systems that are characterized by different inference rules, like the Hilbert system and other kinds of things. So yes, the answer is the fine equational proof uses the Dijkstra-Scholten inference rules for equational logic.
Okay. Okay, formulation date, just a date object. Or missing unknown or whatever.
Would this just be part of reference?
No, it shouldn't be, because you want to do things like make date list plots of things. So it will be part of the reference, but it should also be separated. For these axiom systems, I kind of think that we should do author or formulation? Author, it's now a very Platonic question whether these things have authors or whether they just exist in the world.
So in geometric scene, we called these formulators. And there's also like provers, proof sources, proof dates. There may be other distinctions you want to make.
Yeah, it makes sense to distinguish formulator and prover.
What the hell does it mean to prove an axiom system?
Right. It may not mean anything for this.
I think it means nothing. Okay, this one, I suspect that essentially all of our formulators will be entities, but they're all well-known enough characters to be entities. So they should be people entities, I think. Okay, so having defined this, the other things we need to talk about are axiom schemas, which I think Jonathan has an idea about, and also, well, anything else that's come up. Let's take a look down here.
Without wanting to derail the conversation too much, if we're going to start supporting model stuff in axiomatic theory, it may be worth discussing how this overlaps with the model stuff I did for counterexamples, because it would be nice to have that be consistent.
What is counterexamples?
So actually, hang on, I can email you this. So we discussed this a while ago, but it never got. It's not currently in the build, but there's a. Okay, I've just sent you some code.
Should I just run it?
Yeah, if you run that, and then if you run, I don't know, something like this. So, this is trying to prove a theorem that is false. in this case, trying to show that the NAND operator has associativity. And so the way you want to demonstrate that that's false is by finding an explicit counterexample. So we never finalized the design, which is why it didn't make it into the kernel. But so find equational
might be an interesting thing for Mano to work on too.
Yeah, sure, right. I'm happy to relinquish control of this. But okay, so if you ask for counterexample association, it will show you the explicit multiplication table and the counterexample association. And example should be lowercase.
Oh boy.
And you can also call, there's a bunch of things you can do. So you can also call falsification function, which will confirm to you that it is in fact a valid counterexample.
Okay, I understand. Well, that's nice. All right. We should nail this design as well. I mean,
the main point of discussion was whether this should be find equational proof itself that runs two parallel processes, one trying to find a proof and one trying to find a counterexample, and returns whatever finds first, or whether this needs a separate function. Because one of the main problems in find equational proof is that it may hang trying to find a proof while there is none. And so if it was running simultaneously a search for a counterexample, it might stop once it finds one.
Yeah, I agree. Is that right, Jonathan? I mean, in other words, because I've got some things I'm trying to run right now where maybe I should be trying to run a parallel counterexample checker.
Yeah, I mean, for instance, if you take that specification of that theorem and run find equational proof on it, I'm pretty sure it will hang. I'm almost positive. Yeah.
Well, it will eventually time out.
No, time constraint is infinity by default.
You know, this is Gödel's theorem in action somehow.
Right. But the counterexample finding stuff, if as long as the counterexample is reasonably small, it's pretty efficient. I mean, Jose is right. So the two main design problems that we ran into were figuring out whether this should be part of find equational proof and how that should work. And also figuring out, I think you basically wanted us to be more certain about how we were representing models as a general design thing.
Okay, but this counterexample thing, putting it into find equational proof, that seems like an obvious win.
Right. With overrides, obviously.
Yes. And I mean, what it should do is come back with missing, not true, more or less.
Right. So right now we return a failure object when
okay.
It can show.
Okay, fine. Failure, yes.
Yeah.
Okay.
Like if you do, hang on. Construct an example. Yeah, so like if you do this, it will return a failure. So I guess the point would be that we'd have 3 failure modes rather than 2.
Well,
right
proposition false is this is a failure mode, but then one could have a thing that says that as an opener here that actually gives the counterexample in the summary box.
Yes, right.
Well, I would say that once we find a way to express the counterexample, it would be nicer if we return a counterexample object. It's more useful to keep working with it later.
Yeah.
Well, I think if you ask for a proof, look, a proof is not a count. I mean, what is the point here?
Well, look, a counterexample is a proof. It's just a proof of the opposite thing to the thing you asked for. That's where
Can we put this counterexample thing into the function repository for now? Could you package it and put it in there?
I can turn it into a function repository entry if you want.
think that'd be a good idea. I mean, in terms of the design,
we should get a better icon. That icon is meaningless.
I thought it was some kind of, I don't know. I was thinking some kind of Mycenaean. Never mind.
It was so stupid. I think I made it because I wanted it to be. I wanted to make a cross as a graph, but I picked the wrong graph layout.
Oh,
that's a.
Oh, that's amusing. Okay, all right. But so here, why not? If this was an association, I mean, you're pointing out that axiomatic theory could have some other models that are explicit models.
Right. So I mean, I guess the point I'm making is that in this we are I have implicitly introduced a kind of way of introducing a model, right? That it's a list that contains, operator arrow and then a multiplication table as a stated as a pure function. And the question is,
Right.
Is that a design we want to stand behind, or should we modify it for axiomatic theory?
Well, notice that what you've done here is you've picked the name of the operator as the left-hand side, whereas here it's the name of the operator. It's the tag of the operator, right? Which is the left-hand side here. Whereas here,
in counterexample, it's the actual operator symbol, whereas in axiomatic theory, it's the string name.
Right. Well, I don't think this is bad, except I wouldn't do it as I would say operator. I mean, I would say, something like operator models arrow center dot arrow. Now, the arity.
Right.
And these are always finite models. Is that true?
Yes. And actually, the algorithm wouldn't work if the model were not finite.
Well, I'm thinking this should be operator multiplication tables. Or just operator tables. And then this could be symbol or variable settings. I mean, we know it's a counterexample because you just asked for a counterexample. That'd be my suggestion.
Except if we do what Jose's proposing, then we haven't just asked for a counterexample.
Well, but I know, but we're returning it inside a counterexample object.
Right.
Then we know it's a counterexample. I think that's reasonable. I mean, why don't you make a WFR that works this way?
Okay.
And I'm not even sure it needs the counterexample object for now. For the WFR case, I would just return the association.
Okay. You don't think that having the falsification function? I don't know. I thought that was a nice gimmick.
What does it do?
You can try it. It's like it's the dual of the proof function. So if you run it, it should say false.
I understand. That's nice. All right, I'm sold on having. Fine, I'm sold on having the counterexample object.
Okay.
Um,
Hopefully with a less dopey icon.
yeah. I don't know why these are colon equals is. Why don't they just equals is? They should all be equals is, I think.
Okay. Even the center dot?
I think so.
Okay.
It's just pure function, right? I mean, and then, yeah, so you just take the operator tables and put the, hash next to them and do that thing.
Right.
Okay. All right. Let me just raise one other thing. Groups. I may be totally muddled here, but how do we take the defining relations for a group and stick them in to the axiomatic systems stuff?
There is a notation for that. So it's axiomatic theory. Oh, you have it there. Axiomatic theory group axioms, quaternion. That should return both the axioms of group theory plus the axioms with the defining relations of quaternion. And it's possible to choose the names of the generators too.
So that's not just a generic group.
Exactly. You can prove things about the quaternion group.
Oh, cool. Okay.
And there is another property that allows you to say generators goes to I, j.
Okay, so hold on. Here, can I put in alternating group 5 or something?
You need the the group theory, the final group data notation, which is list alternative group, 5. But I can update it to.
Yeah, you should update it. Maybe Mano could help with that too.
Absolutely. Alternating group, 5 list.
Oh, I did not know this worked. That's really nice.
Yeah, it was added for 12.1.
Okay, is it consistent with our models idea? It sort of is, right? It's sort of a model. I mean, in particular, we could potentially here, I mean, let me understand the relationship to this 2.3. I mean, in addition to defining relations, we should say, oh gosh, the notation for these defining relations relative to over here. What does that? How am I understanding that?
Yes. So each of these numbers represents a generator, and so in axiomatic theory they get names that are variables. So 2 will be F, 3 will be G, etc. So for example, let's read the first one. So 2 times 3 will be F times G times 2 is F, and then 3 minus 1 is sent to the other side.
Sorry. Hold on. Wait a minute. 3. When you say, I mean, the 1 means the identity. Is that correct?
Exactly. Yes.
Okay. So 2 and 3 are just arbitrary other elements. Is that correct?
Well, imagine that the 8 elements of the quaternion group are called 1 to 8.
Mm-hmm.
And so you ask for the multiplication table, and you get an 8 by 8 multiplication table corresponding to the elements 1 to 8. So
yes.
In that multiplication table, if you select the second and third rows, those are going to act as the generators.
Okay.
It's all synchronized. And so the problem is that in axiomatic theory, to avoid having names, we use letters like we do with all other variables. So F and G will represent respectively 2 and 3. And the convention in finite group data is that all the generating relations are equated to the identity. While in this case,
no, I understand that, but I mean F and G, it doesn't know F and G and A and B from a hole in the ground, right? I could name this anything I want.
Exactly. And you can say, in the same way that we can name the operators, you can say generators goes to list A and J, and they will be called A and J.
But I mean, if I try and prove a theorem, can I name them A and B here, or will that confuse things? Why does it care?
No. It doesn't care because that's why we have formal A, to avoid confusion with A.
Yeah, I understand. But these similarly, this could, instead of F and G, I could use formal A and B here in these relations, correct?
Right. It won't conflict with any of the others because those are quantified.
Right. But I think you shouldn't. It's a bit confusing to read.
I see. So these are the defining relations are not quantified.
Exactly. Because they are explicit elements.
Oh boy. Well, that raises another can of worms, right? Because I mean that's in addition to the model is about, I mean, this is Jonathan's domain of discourse thing. The model is about the operators. The domain of discourse is about what these symbols actually mean.
Right. And this is something else we should arguably discuss. So in axiomatic theory, our philosophy was that the literal elements, like say the identity element in group theory, those are treated as being like operators with arity 0.
Yes.
Which implicitly is what axiomatic theory, well, if you prove a theorem using the group axioms for the quaternions, that's implicitly how fine equational proof is treating F and G.
Right. Mm-hmm. We have an example in the axiomatic theory page if you want to look at it. It's the second application example.
You know, we thought we were giving Mano a very straightforward project here. It isn't. Okay, no matter. Go ahead. Set a second application example.
Yep.
Is this documented, this thing with groups?
I think it is. Yeah, we discussed it certainly for.
Yeah, I didn't read. I'm incapable of reading. That's my problem.
So go to the second one, further down. Yeah, here. And you see how generators are named I and J at the end?
Yes, I do. Interesting. Well, it's not totally silly how that works.
And by the way, gratifyingly, the association is sufficiently similar that this is easily interconvertible with the multi-way algebra stuff.
Wow. It's moving into place, the grand unification of everything, from the standard model of physics to the standard model of whatever to, yeah, cool. Okay. Well, I think this is a reasonable place to go then, is to say you add these I do think, by the way, you should have above the fold, you should have at least one example with group theory here above the fold.
Okay.
Okay, what are we going to do? So Mano is going to work through sort of standard axiomatic theories and is then going to work on, presumably, things like, okay, we've got axiom schemas, which Jonathan needs to define how that's going to work. And then, well, then we've got a sort of infinite collection. So we've got logic puzzles, which, well, go ahead.
Sorry, just one quick thing. I mean, so the way that, okay, the design that I think we came up with for doing the axiom schemas kind of relies on this interpretation of sort of explicit elements as being operators of arity 0. Because what that means is when you're quantifying, in something, when you say, for all ABC, center dot A, whatever, those ABCs are not treated as being ontologically different to the center dots. It's just the center dots have an arity of 2 and the ABCs have an arity of 0. And so because of that, there's nothing to stop you also from quantifying over the operators, because center dot and A are treated as being, as I say, sort of ontologically the same kind of thing.
Yes.
And so, and as soon as we have a sort of a reasonable way of doing that, then we immediately have support for higher order logics.
Right, but that's not the same thing. I mean, that's a different branch than the axiom schemas, I assume.
Why?
How are axiom schemas made from quantification over functions?
That's what an axiom schema is, right? With something like the induction axiom, you can formulate it either as an axiom schema in first order logic or as a single axiom in second order logic, because you're quantifying over predicates.
All right, let's take a look at this. For all B, this is kind of messy, but so you're saying, so what is induction if you write it in second order logic?
Well, if in second order logic, then you're just quantifying over the set of possible predicates.
Yes. Well,
Right,
that's nice. That's a clean way to do it if we can do that.
All you're saying is, for every phi being a unary predicate, such and such is true. And the axiom schema approach in first order logic is to say we'll just have a separate axiom for each possible phi. But you could also just say we'll have phi be a quantified operator. And then that's a second order logic statement, but it's a finitely axiomatizable thing.
Okay, so your point is you can unroll it into a finite sequence. Well, it's an infinite sequence of axioms, but it's a generator. There's a finite generator of an infinite sequence of axioms in first order logic.
Right. So just as we could have a separate axiom for every A, B, every possible value of A, B, and C, but we don't. We quantify them. We quantify over them. So that's why this is a first order logic thing rather than.
I like that interpretation of axiom schemas. Yes.
Yeah. Right. And I think that's. Yeah, I think that personally, I feel like that's the cleanest way to do it.
It is very clean. That's a very good idea. So what we have to do is just call it F dot, and we'll have a formal, formal F, and we'll just say formal F dot. So I mean that would be. We're saying for all formal F, AB, for example, F of AB, whatever it is equals B or whatever the heck it is, right? So that's fine. Looks good to me. That's great. If we can do axiom schemas like that, wonderful.
Right.
Solved.
That requires minimal modification of fine equational proof.
Yeah, it's great. Great. Now, what about logic puzzles? And are we going to represent those as axiom systems, so to speak, with crocodiles and things like this?
So I think there's a strong argument for doing that, precisely because there are so many so the examples that I gave in the documentation were taken from this TPTP database, which have a huge number of logic puzzles that they use for kind of benchmarking things like Vampire.
Okay, but the problem is then if you say, I mean, that's okay, so long as we recognize that there's going to be a whole boatload. I mean, I suspect there's going to be like 30 or 40, axiomatic systems that are sort of universal algebra-like things. Then there'll be, just a boatload of these logic puzzles, presumably. Let's see. Oh, wow. Individual axiom sets for TPTP. Okay, so let's pick a random axiom set. What the heck are these?
So these are generally these things are formulated using the TPTP language, which is based in turn on the Mizar formal language.
Oh, well, let's make an importer for that.
Well, yeah, quite right. I mean, it definitely seems like a good use of time to just write a compiler for Mizar into axiomatic theory.
Okay. I'm surprised nobody's done that.
I did look at Mizar long ago, and it was easy to interact with the first simplest group theory theorems, etc. But then it became too complicated quickly.
But notice that those places will have, like Mizar, will have, named theorems of group theory and so on.
Yes, but they also have a tremendous number of collections of intermediate steps. And then they use some variant of step theory what was it? Something called Grothendieck.
Grothendieck set theory.
Yeah, and so just the minimal variations of things complicate things. At least in what I try to do. So I gave up at some point.
I wonder how these compare to the metamath axioms, which I've been playing with. Well, anyway, so okay, so
the Tarski Grothendieck set theory is also implemented in MetaMath. So at least at a formal level, they should be interconvertible. I just don't know how different the language is.
yeah, but I wonder whether they've got. I mean, there's like 43,000 theorems in MetaMath, which I was playing around with, and I wonder whether this has more or less, or it doesn't seem to have them collected as well. But okay, so there are a bunch of axiom systems, and then there are well, okay. So I think Manu needs to go look at these, but it seems like that's a good source there. Syntax and BNF. Okay, that's a good sign. It's also possible, I think, Nick just did that nice work on MetaMath importing.
Well, if we can have an importer that actually imports in a formal style that can be fed into find equational proof, that would be pretty cool.
I think we can. Don't see why we shouldn't be able to. All right, I need to go. I'm supposed to be doing something completely different here, unfortunately. Right, unfortunately, we didn't get to these other things on the agenda today. I think we have to do that another time. But Devin, this is, you know where to find this file. You can give it to Mano. I think Mano has a bunch of things to do here. Should be off and running. That is great. Fine. All right. Anything else for right now? Oh, okay. All right. See you all soon.